Hello, everyone, and welcome back to HDL for Digital System Design. So, topic 2 here, talking about combinational building blocks. We're going to start focusing in on some of the nitty-gritty nuts and bolts of actually leveraging Verilog to get things done. So, we're going to focus with one of the things that we see in a lot of different languages, data types, and also extended versions, vectors. So, without further ado, let's push forward. So, no matter what code base you look at, you're going to start off reading and trying to figure out how things are declared. So, you're going to see a whole bunch of messages usually in historical code bases about the uses of wires and registers and how those all function. Understanding that is going to be critical for a lot of the things you do, and um, let's just take a look at it now, get it out of the way. So pretty much every lab you do and pretty much everything you do in RTL, it's going to end up using vectors of some kind. So, an 8-bit vector or 32-bit vector, you know, great common examples, but we're going to see plenty of those. What do you do with vectors? You end up concatenating them. You end up using them to do sign extension, which you'll see in topic 3 for discussion on our ALU. You'll see it in topic 9 when we talk about addressing memory spaces. You'll see it when we talk about UART. You're going to see it everywhere. So let's talk about that and make sure that we're on the same page. So you open up any project that's out there, whether that's OpenTitan or otherwise, it doesn't matter what you find. You're going to see at the top of every module, you're going to see some definitions that involve wires and registers. And part of the reason why this exists is actually just where Verilog came from. It's a historical legacy. Um, there have been updates to the language, well, actually, technically, superset language system Verilog that provides additional functionality and tries to remove some of this ambiguity and issues with the naming by introducing another data type called logic. But in general, you're going to have to access and read legacy code. And so understanding the difference between wires and registers is going to come in handy. So with that, um, when you might think, oh, I see the word wire, and that means that it is just a wire signal from A to B connection, no storage. And you might then read register and be like, oh, register, that means storage, right? We store things in registers. And so you might say, oh, well, I want a register or I want a flip-flop, right? A storage element. So I will use the keyword register. Like that's a natural thing you might think is true. Unfortunately, that's not the case. Wire and register are basically syntax categories. They're not hardware categories. The name itself doesn't actually make the synthesis engine do anything, right? At least not in this particular case. So when you say wire, basically what you're saying is, hey, this thing is assigned continuously. So whether that's an assignment or in a module port, you can basically think of wire meaning that this thing is just permanently connected. Versus register is something that's assigned procedurally. So procedurally should invoke some thoughts of like your typical programming spaces, but it is not always the case that that register will equal the same thing or be assigned to the same thing. It is procedurally set on what it will take. Normally, this should, and I mean, it should reside within an always block. So we'll talk about those in more detail over time, but that still leads to the question of, whether or not there's storage assigned to this register element or not. And it actually depends on context. So you could have this thing that you've defined as a register. It will become a flip-flop depending on if there's a clock edge or not. So flip-flops are clock driven, right? They store a value at a specific instance in time on a clock edge specifically. And so if it doesn't have a clock edge involved, it might not necessarily become a flip-flop. So let's look at a little bit more into that. So here's the idea here. You can have a register that gets synthesized as combinational logic, no flops. You can have a wire that drives flip-flops D input. The name ultimately tells you how it's assigned, not what the hardware actually becomes. So created this example here. And so we'll go take a look at it here in a second. But there are essentially four declarations, four sets here. Number one, here we see a wire that will result in something that's always combinational. So the wire is 8 bits wide. It's called wire underscore sum, W sum. And what we're doing is we're assigning it to the summation of A and B. So this is continuous, it's an adder. There's no clock involved. There's no register involved. At any instance in time, W sum is essentially the summation of two independent signals, whatever they might be. Number two, we have essentially something that we've defined as a register, again, 8 bits, called our counter. And it appears that at every positive edge of a clock, the value of this counter is incremented by 1. So you can kind of see that right here, that essentially what we're saying is at every positive edge of the clock, we want to increment the counter value by 1. So this will result in a flip-flop or a set of flip-flops, 8 of them, that at every clock edge, the value within this structure, the larger structure, increases by 1. And we will store that value. And the next clock cycle, we will look at the current value and add 1 to it. So register flip-flops definitely exist. Number 3, we now have a register that essentially says it's a 4-bit one. And it's called R mux out, always at star. So basically what this means, this is a sensitivity list here, wherever you see the at, basically says anytime I see any signal that I care about, we will work on it. So star here would mean if I see a change in select A or B, we will execute this this space, or we will this logic will work. And so in this particular case, there is no flop. There's no storage element here. There's not a clock here. All that's happening is combinational logic that is essentially running. Anytime any of this changes, our mux out will change. So notice here, register that doesn't actually lead to a flip-flop. Last one here, and this is an interesting one, but we have here essentially register that is 4 bits wide, and named it R broken because it is actually. Sensitivity list, same as before, at star, but there's an if check here, and it's super interesting. So if enabled, then we say R broken equals data. Well, what's super interesting here is there's no else statement in this. And so what actually ends up happening is this will synthesize, well, I shouldn't say that. It is interesting what will happen here. It will create a latch. It will create a flip-flop here, which might not be what you expected, right? In this particular case, it's not likely the behavior that you were expecting. So if we back up a little bit, I will use the W underscore and R underscore prefixes personally. For me, note the synthesizer, right? The synthesis tool doesn't care what I write. It does not care if I use W or R. But if you are reading this, you want to know how it works. So case number 4 here is a bug. You'll probably see it, and we'll talk much more about it in video 3. But let's go take a look at the lecture examples here. Note that all 4 cases are in one module, and we'll be able to go and explore that. So you're going to navigate to lecture examples, week 1, day 2, and then it's day 2, S1, example 4. And so let's go take a look at that. All we'll need to do is a make sim and a make stat just to see. So with that, let's take a look. I'm gonna pull up the terminal here. So what I have here is I'm inside of the directory that we care about, which is essentially the HDL for DSD directory. I have not yet run our nix command, and I can verify this by if I try to type in iverilog, I get nothing. So I can type it all the way out if you'd like, and notice that it's not found. So remember that the thing we have to do at the top of our, when we enter first, is we need to do a nix develop. Run that. Depending on how much you've installed in the past, this takes a little bit of time. You'll then get output here that includes essentially all the tools that have been installed. Yosis, again, the next generation place and route tool, Ice Storm, iVerilog, GTK Wave, and Emacs. Also, you can check the README in each of the project directories for a little bit more details. So we want to go check out the lectures. So we can see right here at the top, we have a lecture example directory. And within there, we have essentially all the days. So we can go to week 1, day 2. And our example was going to be in day 2, slide set 1, example 4. All right, and in here, we have again this wire versus register. We can take a quick peek at this if we want to. So essentially, it's exactly that code. And you'll see that we can do a make sim, make wave, and make stat. And get some fun output here, but it should render nicely when we print it out. So what we end up seeing is all 4 of those cases back in here, the exact same way that they were in the previous code, just a little bit more, I'll say, decoration around it. So what we can do is we should be able to do a make sim. It'll run. It will show us that we have a handful of test cases that are being run behind the scenes. We are able to add numbers correctly. Our mux works as expected. We're getting a latch that is showing up in case 4, which is what we expected, and case 2 increments by 1 at the every clock edge. So all of our tests pass, none failed, but we are basically showing that for case 4, a latch is being generated and created, which is not the behavior we expected necessarily. I'm going to run make wave here, but we're not actually going to be able to see it in this terminal window right now. So let me see if I can add it in real quick for us. Let me switch this for us. And let's do the GTK wave for us just to see it. So here is the GTK waveform viewer. And you'll see that we have our test bench here. And the reason why I'm showing you this is that when you use the Nix develop that is bundled with all of this, you'll have direct access to GTK Wave. So just showing off that you don't need to use VS Code, all of this should be enabled as well for you, though you're more than welcome to. Up next, we can view any of the signals we want. This will be quite large here, but that's okay. So this is just every single example we have. Cool thing about GTK Wave and other systems is that you can actually change the data format for a lot of these. So you'll notice that there's a label here. Tried to make this convenient, actually use Claude to help enhance the output of this test bench so that this is not something that you normally see in test benches, but with the power of Claude, we can do it. I'm going to change the data format here to ASCII. It should work. So you got to make sure it's highlighted and select. And now if we resize this a little bit, what you'll notice, let me zoom in now too, you'll notice that in line, without having to go back to the code, we can see exactly which case is being run through right now in the test bench. If we look at 16 nanoseconds here, and we'll go back in a moment, we can actually see everything that's happening. We can see how our system is actually working. So our adder here that was supposed to take in hex value of 12 and 34 here and give us 46. We should see that occurring and summing up correctly. Let's take a look. Right. So we have 12 and 34. That actually might be right here. Might be off a segment. There they are. 12 and 34 are right here. In this previous segment, you can see those. And then the sum of these should be 46. And let's see where that's getting latched in at the very bottom here in sum. So let me highlight these for you to show you that this is, let me highlight them in blue all the way around. So, and the sum down here. So what you can do is you can go through and compare what is happening in your code versus what you're seeing in the output. If we go and we take a look at the case select, right, where we're setting essentially select equals 1. If it's 1, we're going, the 4 bits of A are being selected. Otherwise, it'll be B. You can actually see the two different cases here for the mux at the top. So we can basically trace that as well. So the mux output here, let me make that for now. Let's do orange here. Nope, that matches too much with the red. So let's try indigo. It's too purple. Sorry. Let's find one more. Maybe cycling the color will help. Let's do yellow. Okay, this yellow line here, mux, and actually maybe I can even make it bigger for us. I can insert a blank before and above it. So mux output here, you can see this mux output, and you can see that it is driven essentially to the value of A when the select is 1. So we can look at iSelect. iSelect is set to 0, which means we should be getting the value of B. So, well, here's 1 right here. And what value are we getting? We get the value of A out the moment it drops, right? So if we look over here, it drops during this time period, right? Here's the select all throughout here. I'll highlight this one also. When it's 0, we expect to see the value of B, right? And that's actually the value we've encoded in conveniently. And you see that that's the output as well that we see here. So all this to say, you have access to quite a few tools here at your disposal to investigate the output of simulations pretty easily. And so that is a quick overview of looking at this example of different mechanisms, different assignments of wires and registers, and how we probably should take a moment. And actually, we have a flow chart that we could follow. Let's take a look for basically understanding what's going on. So if you are trying to make a decision on whether or not a signal is supposed to be a wire or a register, first question comes up. We have a signal and it needs to be assigned somehow. Question number 1, is it driven by a sign or a module port connection? Like, how is that happening? If it's in one of those two places, it's going to be a wire. If it's not, then it has to exist within an always block, which means this thing will always happen. If it's not, you probably have a problem. So, but if it is, right, if it's inside an always block, then it's probably a register. And then you've got a question to ask yourself. Is there a clock involved? If there's a clock, then you're generating flip-flops. If you're not, you're getting combinational logic and no storage. So the big takeaway here, a register does not always mean, or reg does not always mean register. It really does depend on the sensitivity list. When is that reg signal being assigned? How is it being assigned? All right. So you can go back and look at the 4 cases and follow the flow chart. And what you should find is that 1 is a wire, 2 is a register with sequential logic behind, 3 is a register with combinational logic, and 4 is a register with combinational logic, but it's broken, right? Essentially because there's this else that doesn't exist, so it doesn't actually fit nicely into any of these. So System Verilog's logic type does fix this. It collapses this branch into one. And so you don't have to worry about which keyword to choose, but we'll get there later. Okay, so something that you're going to see throughout the rest of this semester is this idea of vectors. So right here, what we have are 2 wires that are defined. One is an 8-bit wire called W data. It represents an 8-bit bus, where 7 is the most significant bit, 0 is the least significant bit. We also have defined a nibble, basically 4 bits, 3 to 0, 4-bit bus. You can access individual bits, right? So once defined, WData 7 will give you a single bit of WData. It will give you the most significant bit. You can also do ranges. So you can do WData 3 to 0. And you can also do WData 7 to 4. You can grab actually any subset that you want. So please use the convention most significant to least significant bit when you're grabbing things, with the least significant bit being 0. You could do it ascending 0 to 7, but please don't do that. You can imagine that, normally when you look at bitwise representation, right? If you saw 0, 1, 0, 1, you would read that as 5 naturally. But if you start flipping your bits 0 to 3 with your least, it becomes very confusing to the reader, in terms of whether or not that is 5 or whether or not that is basically the reverse of that, right? Is it actually 5, or is it 2 and 4 is it 6, right? Or what is it, right? So what else can you do with vectors? Well, you can concatenate them. So you can take a wire and you can, with 2 nibbles, for example, right? If you had nibble high, nibble low as previously defined somewhere, you can concatenate both of them together to create an 8-bit value. You can also use it to do replication, right? So if you wrap essentially in parentheses some bit pattern, you can repeat that pattern however many times you want. So this second line here, where it's 8 and then open parenthesis or open curly brace 1, basically 1 bit, that is going to repeat 8 single bits. You can also use it to do sign extension. So it's a combination of these two in a way, right? The first part here does an extension. It does 4 times the most significant bit of the nibble, and then concatenates it with the rest of the nibble. So this is a convenient way to do sign extension. So you can mix and match. So you have concatenation, which is just in curly braces, you basically put the things you're concatenating. If you are replicating, essentially the pattern is curly braces, and then within it, the number of times you're repeating, followed by in curly braces what you're repeating or replicating. So you will use sign extension a lot in the ALU, in math, instruction decoders. And so this is essentially what it looks like. The inner part here is the replication part. Repeat whatever bit you want n times, or set of bits technically, and then your signal, and then overall this is a concatenation. So get used to it. All right, so your turn. Predict what's going to happen here. We have two nibbles, A and B, that are each 4 bits, and we are concatenating, replicating, and doing a sign extension. So what do you think the answers are for each of these three, for concat, replicate, and sign extension? If you want to pause the video and try to predict it, that would be great. All right, so what ends up happening here? Concatenation is literally just nibble A followed by nibble B, and you basically see that. It's no surprise there. Hex representation here is D2. Replication is just whatever A0 was, so A0 up here would be the least significant bit. It's going to be a 1, replicated 8 times. And then finally, sign extension. We're going to take, looks like 4 times nibble A's most significant bit. So most significant bit of A is also a 1. We're going to put that first, followed by nibble A. And so we get all 1s followed by 1101. So pretty straightforward. I recommend you try these out. So we can go take a look at some vector operations inside of, let's see, lecture example, week 1, day 2, S1, example 1. So let's open that up real quick for us and take a look. So let's try. All right, so all right. By the way, you can in most of these directories, you can run a make clean to remove old information and data. But let's go back. We're going to go to day 2 S. We said S1 example. Here we go. So we have in here vector operations. So we can take a quick look at this. Day 2 vector ops. And what we should see in here, all those nibbles. We have handful of convenient assign statements to get most significant bits, upper and lower segments, and then some different operations, concatenation, replication, and then a sign extension, which is essentially, again, a combination of concatenation on the outer edge with replication as well. So those are the things we have internally. So concat, replicate, and sign extend. We can also take a quick look at, we can look real quick at one other thing here. Let's take a look at the test bench just to see what the test bench is doing. So this test bench is going to instantiate the vector operations design under test, right? So the vector ops that we just defined, we looked at. It has all the inputs and outputs that we just saw, all defined. Remember, this test bench wraps around our world. It's going to count the number of times we see a failure here. And what we basically see here is, unfortunately, a rendering that is not exactly what we want. But that is, again, an issue with just how it's presented and rendering in your screen. This triple equals with the not in front behind the scenes is actually a not equal. All right, so just be super careful about that. It renders differently in different spaces. This is my terminal being a little bit over aggressive. So basically what this is going to do is it is running through a handful of cases where it's putting in some inputs and expecting some specific output. Again, this is just set up to verify that this works as expected. For now, don't worry too much about the test bench, but know that we are testing the concatenation, the sign extension, and all those things. So we are going to come here and we're going to try to do a make sim and see if that works. And what we get is we do get it passing, which is great. We can view the waveform as well. We can also look at some statistics. So just in the interest of time, showing you that we can look at statistics, number of wires that were created, number of ports that exist. Um, Basically, we can go through and double check. We can even see how many LUTs were used. And so this might be interesting to you. We just did a lot of manipulation of signals, but we didn't use any lookup tables to do it. So that's perhaps interesting. So let's go back. And yeah, so basically explore that for a bit. We can look, like I said, of what was built. And what I had mentioned at the very end there is that there aren't any flip-flops or LUTs that were needed. So everything we were doing all surrounded pure wire reroutings. Concatenation and moving signals around is not logic. When we talk about replication, that is fanning out. It's taking one piece of logic and connecting it multiple places. Bit selection is literally just picking specific wires. No logic involved there. So there's no gates. This is just relabeled wiring. So concatenation, replication, sign extension operators might look like code, but in synthesis, like to synthesize it, it is basically, it's only wires. It doesn't consume any flip-flops. It's, in quotes, free. So there you go. So you could check the machine. I suggest you do whenever you get a chance. You could ask it, given wire 3, basically a wire that is 4 bits long, right? A vector A that is 1000. What is essentially 4 times the most significant bit concatenated with A? What does it evaluate to? And how many gates does it synthesize to? So you could ask this prompt directly. You can do a prediction, right? Do you predict that it will be 4 ones followed by 1000, right? And does it need some logic to replicate 3 bits? What you might get out of an LLM might say, might get the value correct, and then it might say a few LUTs. But what we just saw is that's not the case. It should be 0. So replication, again, is wire fan out, not logic. AI might overcount this. Always run Yosis yourself. Trust the stat function. Basically, if you get a discrepancy between an AI model and basically Yosis is going to win, right? It actually knows the gates that it needs. Right, so big takeaways for this. Wires are driven by assigned statements. Registers are always assigned in always statements. Registers, or reg, does not always mean a actual register. The context matters. If there's no clock, that thing that you've done is probably not a register. Vectors, pretty important. They're going to exist throughout everything we do. Nomenclature, normally, most significant bit down to least significant bit in descending order like that. Concatenation, replication, sign extension are free. They're literally wire rerouting. No gates involved. All right. If nothing else, remember the type name tells you how it's assigned, not the hardware it becomes. All right. So with that, next time we'll talk about operators. You just saw essentially the fact that we get a lot of things in quotes for free. Video 2 of this series is going to show you the exact opposite end of the spectrum, where basically math, arithmetic, and comparison operators do consume real LUTs, and they will, at the end, give you some hardware cost. So that will be our focus for the next lecture. So we will see you then.